Salam.
Okay, thank you for coming quite early compared to your other friends. I hope the other will come soon. So in regards with the final exam, actually, the material will be after all the material that I give you after midterm. So you don't necessarily need to study using the material before midterm. And it will be open book, so you don't need to worry. And don't forget about the schedule. It will be on January 5th. I think it's 8 a.m., which is the first a period, yeah, first schedule. And wow, the other come. And regarding the final projects, don't forget to submit the both presentation and also the report to the Google Classroom. And during the presentation, just show the face, yeah? You should have your camera on. And once you submit that, then I will count it as a absence, the presence for additional class. So today's will be 13th class and we need 14th meeting in total. So once you submit that, then it's going to be a 14th meeting. And today we will talk about specifically about the cell manufacturing. So previously, when we talked about the layout, the facility layout, we learned about several types of layout. We learned about process layout, we learned about the product layout, we also learned about fixed layout, and I'm sure you still remember because that's your midterm, yeah. And when we have a several type of layout, we also have hybrid layout and also a specific one called the group technology. And the cell manufacturing is the application on how we actually can do the group technology type of layout. So today we will focus on that and the advantage using this type of layout, and also how we actually can transform or kind of like relayouting our layout and turn it into a better layout by using the cell manufacturing. Okay, so when we talk about the group technology, it's kind of a philosophy. It's how when we try to grouping or clustered a similar product that have either similar design or a similar manufacturing characteristic. So when I talk about manufacturing characteristic, it's mostly about how that they have the same process or they have the same machine, although maybe the sequence is different, but they share the same machine. So we can actually group that into a group product. And one of the application of group technology is basically we try to group the machine. So after we have the group of products, we will group the machine accordingly, yeah, according to this type of product, so that we have the cellular type of a entity. So you will say it as a cell because it will be kind of like a group of a machine from there. And why we do the cellular manufacturing is because when we have a variety product, or maybe the product is one, but there are many parts that we need to produce or to make in our facility, then having the cellular manufacturing will help us to basically minimize the movement. Why? Because if we use the typical layout, then there will be a high possibility that there will be a lot of movement, considering that we have a lot of parts. And grouping this product or a part into a family and then group it the machine that we're gonna use into the cell layer or the cell will affect to the space and how each part or each product will move inside the facility. However, of course, it's not easy to do that because there must be either constraint or a way actually to do that. So the CM or cellular manufacturing can be called successful if and only if the new layout can basically reduce the material handling cost, reduce the movement, whether it's inside the cell or between the machine inside the same cell or between cells. So I will talk about what is intercell and intercell later. And according to the literature, actually the use of cellular manufacturing can help to reduce several ways in our facility, including the throughput time, the setup time, and then the inventory, in working process inventory. And in the end, by having a better layout, we can actually reduce our material handling costs because we have not fewer movement, but shorter movement. And it is actually from the literature is also say that we can increase the quality of our product by having a better layout with the cellular manufacturing. And in CM, we will have two types of terms that we will use. The first one is the part family, and the second one is the machine cell. So when we say PF is the collection of the part or the product that is similar, either it's the design, the shape, or the manufacturing processes. And we will have the machine cell term that is actually the cell itself or the group of machine that used to process the PF or the part family. The important thing is that because we will have kind of like machine sharing or workstation sharing, if we talk about workstation, then the capacity should not exceed the total capacity, the total production for all part process in those particular machines should not exceed the engine or the machine capacity in each cell. And then basically, if possible, then the use of the CM itself should not the size and the number. It means the space utilized and the number should not exceed the value set by the user. So for example, the user only wants 3 cells. So we will try to make only 3 cells. And if having 3 cells is actually impossible, then maybe they need to reconsider not having the cellular manufacturing or CM and rather use the traditional layout. Now we will try to understand more about the CM or cellular manufacturing by looking this figure actually. So we can see this in a job shop environment when we have several type of parts. Okay, so in job shop environment, we have many parts or many a variety of products that we need to make, right? So for example, in this case, we have 10 parts. And actually, I already helped to categorize. So the red one is the root, how to say that? Root parts for part 1, part 2, and part 9 here, where they move from the turret machine to drilling machine and then goes to the brushing machine before going to, I don't know, maybe quality check or something. And then we have the second route used by the 4 parts. And as we can see here, it's from TM to DM to the milling, back to TM, and then back to DM before they are going out. And the last one is a part for part 5, part 6, and part 10, where they move from the turret machine to the milling machine, to the drilling machine before going to broaching, and then left the whole facility. Okay, so if we see here, according to the layout, what kind of layout actually used in this job shop environment? If you still remember, or you still remember? What, Mohsin? I can't hear you.
Can you repeat the questions?
What type of layout is being used in this picture?
Oh.
Is it fixed layout? Is it product layout? Is it process layout?
Process.
What?
Process layout.
Process?
Yes.
Sorry? Yeah, that's correct.
Because it's a job shop. So
yeah.
Shop is process.
Yeah, good. So if you see here, in the job shop, thank you, Mohsin. So if you see here in the job shop environment, actually we can see that the machine is being grouped according to the same type of machine, right? And then the movement is based on the process for each part. However, if we see it like directly right now, according to the movement, what makes it not really good layout? Is there any opinion? Maybe Dicky, do you have any opinion? What makes this current layout is not, maybe rather than not good, it's not optimal kind of thing, or not efficient? Are you there, Dicky?
Yes, Miss.
Yeah.
I'm still thinking about it. Miss?
Yeah.
Is it because of the route, the pattern of the route that we see? It's like, how to say, like chaos like that? It's not structured.
Yeah.
Organized well like that. It just go and coming back again, and then go again there, coming back again, and then to the next.
Yeah. That's a really good thinking. So if we, thank you, Dicky. So if we see here, so particularly for the brown route, we can see that there are many backward, we call it something like that. So from the turret machine, they go to drilling, they go to milling, then return back to turret, and then they go again to drilling before they left the overall facility. And if we talk about only one part, then maybe that's still okay, but we are talking about 4 different parts here. And during operation, then maybe it's gonna be, like Tiki say, kind of chaos, kind of complicated when you kind of have lots of movement inside the same facility. And that's why, although the process layout is good for a typically high variety of product, then the movement should be also considered. And that's why there is a CM, or cellular manufacturing, to help to understand to rely out our facility better by having the same group of machine to basically process the same part family. Yeah, maybe you can also do that. So usually in job shop, when you are talking about job shop environment, and then you're talking about scheduling and how you actually schedule that, then we try to minimize max span. When we are talking about facility layout, we are talking mostly about the material movement, the people movement, and how actually we can reduce that. So by having that, by reducing all this movement, we are reducing the production time. So at the end of the day, not only we are talking about the scheduling inside inside the overall facility, but using cellular manufacturing, we actually can make it simplified. We can simplify all those complexity inside the job shop environment. So for example, if we compare that the process layout with this, we can see that actually we can group all this. We can group a dedicated machine, yeah, according to their group of parts that being made, something like this. So for example, we have 1 and 2 and 3 kind of like cluster or group according to the process. So we are just basically layouting our facility according to the machine process. So when we call it, like say using the CM or the cellular manufacturing a term, then we have 3 different part family, which is the first part consists of part 1, part 3, and part 9. And then part family 2 consists of part 2, part 4, part 7, and part 8. And then the part family 3 consists of part 5, part 6, and part 10. And according to those, each part family will have a dedicated machine cell. So we have 3 machine cell 1, machine cell 2, and machine cell 3. Something like that. And if once we do the relayouting, we will understand how that using cellular manufacturing, we actually can reduce this in intracellular. So inside each cell, we can reduce the material movement, right? So minus. So because you move rather closer, shorter distance compared to this. So when you group it like this, then you will have a long movement from one machine to another machine. Once we group it into each machine cell, then we can actually reduce what is the most noticeable here, that we can reduce the intracellular one. And even if we have a, let's say we will have a additional machine here sharing for each machine cell, then we can still have a reduction of the intercellular. So this is gonna be the kind of like easier, how to say that, the easier illustration, yeah. So we can compare it directly. Well, when we use the process layout, as you mentioned, it's kind of chaos here. Once we change it into group technology layout, it makes it better, yeah. Because there are not many complicated movement or complex movement inside the facility. How we actually can conducting the cell manufacturing system in our facility is by having the part machine process indicator matrix. So what is this indicator matrix? It's actually a matrix for part and the machine with Aij as the kind of a variable where it is equal to 1 if part I is processed in machine J. So this is the machine is the J and part is the I. So for example, this one, what A11, yeah, A11 equal to 1. It means that part 1 is being processed in machine 1. And A14 means that part 1 is being processed in the machine 4, and etc. So the dash 1 means it's 0. It means that they are not being processed in this particular machine. And several algorithms can be used to actually do this reorganization of this indicator matrix to show us which part is actually should be clustered or should be grouped together into the cell manufacturing. So for example, if we see here, so regardless how to, we see that part 1 and part 3 actually share machine for M4 and M6, while others does not. So they can be grouped together. And then for part 4, part 2, part 5, and part 6, they have somehow a how to say that, kind of like either 1 or 2 share machine. So for example, the machine 2 is being used for part 2, part 4, and part 6, and machine 3 is being used for part 2, part 4, and part 5. And because they are kind of overlapped, then decision maker then decided to just put it into the same cell manufacturing. How do we evaluate whether our cell manufacturing is better or not? Is by calculating the material movement cost. Yeah, so it's quite mathematical, like we already actually learned before. So let's say we have a different type of indicator matrix here, where it's a bit complicated because when we see here, yeah, then part 2, actually, this is a different indicator metric from before, you should remember. The part 2 here actually use also machine 1. However, they are not overlapping with the other machine, but they use the other machine like M2, M3, and M5 that being used by other group cell layout. So in this case, then I will just skip this. This is not really important. In this case, then maybe there are several revisions that should be done by the decision maker. So there are several alternatives. So for example, the part 2 is being subcontract. So why? Because if we force the part 2 to be made in-house, then maybe it can be quite costly according to the design of our cell manufacturing layout. Or maybe we can add more kind of like more machine. Yeah, for example, we provide M1 in each machine cell, or rearrange the intercellular movement for the use of machine 1. So for that, it's gonna be a bit complicated because we kind of do it like the with the trial and error. So for example, like this is the current illustration considering our indicator metric before, where we have part 1 and part 3 into one shell, yeah, like this, and they share the same machine. So for example, for P1, they go from M6, M1, then M4, while for part 3, they go from M4, then M6. And then in the other cell, we have 4 different parts that we should make. However, as we can see here, it becomes dependent cell because the part 2 also belong to machine cell number 2. They still need to go to machine cell number 1 and use and share the machine 1 with part 1. Or actually, we can improve it by having or adding additional machine 1 into the cell 2 to accommodate this part 2 being made on the different cell with the machine cell 1. Yeah. So this is the alternative how to do that. So it's gonna be an independent cell where they are not related to each other, or like it's mentioned before, we try to either modify the part 2 routing or rearrange the row and column. It means the location. So it's gonna be something like this, where we have a shared machine, but the location of this machine is being moved so that we can minimize the movement between cell and also inside the cell, so intracell and also the intercell. But however, of course, this option is gonna be different type of dependent cell. It means that later on, maybe you can learn about the scheduling on how actually should this part go first or should this part go later, something like that. And to do the GT or group technology, there are several basic methods that we can use, including the classification and also the cluster analysis. So for classification, it is more about when we group our product. So because it's still the group technology, it means what we group in the classification method is actually we group the product. So that's why we can use a type of visual method and also the code method. So you make a code and then you basically classify it based on the code that you already have in-house. Or we actually can do the cluster analysis by having the metric formulation. So in metric formulation methodology, we will use these indicator matrix a lot to actually rearrange our facility and build the group technology. And today we will talk about these two and also the metric formulation, which is ROC, and also similarity coefficient. You can also learn about other if you're interested. And if you cannot find it on the literature, on the book, then maybe you can also find it on the kind of like a journal. Then maybe they will have a better explanation, because some of these methodologies actually developed by some researcher, and they first submit it or publish it into a journal paper. And other way to actually do the group technology is by model it as a p-median problem or generalized p-median problem. So it's more like the location problem. So if you are familiar with optimization, and one of the topic in optimization is actually how you decided which location considering this type of objective, yeah, the p-median. Or we can have the graph formulation to do that. However, this class, I will focus on this, the 1 and 2 and 3 and 4. So in visual method, it's quite easy, should be, because they mention it as a semi-systematic procedure. So they basically just group the product. So in visual method, we are grouping the product into their common geometric shape. So it's gonna be easy if the geometric shape is easily recognized. Yeah, I mean, like if it's a triangle, then it's triangle. If it's prism, then it's prism. If it's a what's cubic or cuboid, then it's gonna be easy considering the geometric shape. But obviously, when you have a weird type of shape, it's not gonna be that easy if we just relying on this visual method. However, for some expert, they actually can understand the type of process that's being used for a certain type of a product. So I think for this method, you need to be quite expert before judging this group, the product group based on this. And the second one is the code method or coding method. So if in visual method, basically we are only looking for a shape. In coding method, we are breaking down all the product into several different classification, and then we kind of make a code or a numbering or a label based on different type of a classification. So it can be the geometric shape, it can be dimension, it can be the material types, it can be the number of the hole, for example, it can be the tolerance, and etc. So there are no how to say, the limitation on how you will do the code. However, probably if you are later on working in a company, they will have a certain way to code this. I mean, like they will refer to a usually a big company way to code something. And then for the coding method itself, you're basically first you need to build the code. It means that you determine the symbol, the number, and then you will be a kind of database for each symbol that you make. And after that, you will label all the product based on those a rule, the code rule. And from those code, then you certainly need to do the classification. And you use the code that you already make and you already put like something like that on your product or part, then you classify it into different family part or part family. The good things about having the code is that because it's quite, although you will need to have a quite database for that, but later on when you, let's say, having a new product, and then you need a certain, let's say, database about how to process such product, and having this code as the classification way, it's gonna be easy, because then if you have a certain label or almost similar label, then you will understand, you will already have the database on how the product being made, the workmanship. And later on, it's also have if help in the production system, because then you can easily, let's say, make the additional process or route inside the facility. And however, like the visual method, the coding and classification system is actually only useful for a differentiate the part. It means we only make the part family rather than having the machine cell. So you're not really actually designing the cell or manufacturing system, but rather in visual and also the coding method, you are a kind of like cluster the product based on the rule that you make. And although sometimes it's a, how to say that, so when we try to build the machine cell, we are doing it by actually grouping all the part family together, right? Actually, and it can be it's gonna be okay if your production system is not that complicated. However, if you have 100, let's say, or maybe just a 2-digit number of parts, then it's still gonna be quite complicated. And then the coding and classification cannot help you to explain how the machine will be grouped, something like that. So that's why they say that it's not for designing the CM system, but rather just the classify the product into the part family. And for the coding itself, there are 3 types of code, which is hierarchical codes, non-hierarchical, and also hybrid codes. So in the hierarchical, we made the code, we made the rule based on the hierarchy. How you made the hierarchy is up to your company, and each hierarchy will explain a different type of classification. So for example, for digit 1, we are talking about the materials. And then for digit 2, we are talking about the probably shape. And then for digit 3, we are talking about, let's say, the number of holes. So even you don't know what product is this, right? So Although it's a quite easy, yeah, it means that you only need a few number of digits. It means that you don't necessarily need to have a big database to actually have this code. However, like I say, it's quite difficult to translate, because if you talk about the product that is round and straight with a single true center hole, it's not going to be easy to understand what product is that or what part is that, unless you are working super long in this company or you are the one that make the monocode system, the system. And the polycode system is actually being made without the hierarchy. It means that you basically arrange the digit randomly. So you can have, for example, for this one, you can have the first digit as the material, and then you can have the second digit as the shape of the material, and the chemistry and the quantity and how the surface finish. And obviously, having the polycode system, you will need to store a lot of information. However, yeah, you will need lots of you need more digits to store the same amount of information compared to the monocode. So which one is better? It really depends on the company. So and then the last one, there is a hybrid code. They mentioned that in hybrid code there's gonna be a hierarchy and non-hierarchical codes. And how they do it, it's really depend on the company, like I mentioned, whether they will use monocode, whether they will use polycode, or whether they have hybrid code. It's on their system. So probably if you want to have, like for example, actually company can have, for example, 2 digit, the first 2 digit gonna be a hierarchy. So for example, you have the materials, and then we have the shape, something like that. And then after that, so it means that you will have 1, 2 code that is hierarchy, and then the other code will be non-hierarchy. So it can be done something like that. So because you will need to have a better explanation for your part or product. So but you need to save lots of let's say storage on your database. So you decided you usually company use this hybrid method. And then we move to the cluster analysis. As I mentioned before, in cluster analysis, we can actually have a metric-based calculation one, the mathematical programming, or the graph formulation. And for doing the cluster analysis, is actually you can actually do it physically. It means that you move after you cluster it, then you move or rearrange the machine to change the location, or you basically will just you already group the machine, you already have the cluster, but the position of the machine are not changed. So this is the difference. Yeah, so for example, we have 5 parts that needs to go to a different 6 machine, and then according to the machine that's being shared, for example, the part 1 use machine M1, M2, and go out, while machine 2 used M2 and M6, and we can see here that M2 is being shared by part 1 and part 2, while the M3 is being shared by part 3, part 5, and M4 is being shared by part 4 and part 3. So according to their sharing machine, and then we try to group it into the parts. So part 1 and part 2 is decided to be the first PF, yeah, like this. And then part 3 and part 4 and part 5 is the part family number 2. So in physical layout, physical machine layout, they will move this layout, they will change this layout into different machine cell like this. So the part 1 will go to the part 1 and part 2 obviously will just go to this, and they will have intra movement here without the inter movement, inter cell movement, and then they will just go after finish, while the part family 2 will go to the machine cell number 2 like this if we change the location of the machine. But in logical machine layout, we already group it according to part family. However, maybe there are considerations. So moving the facility or moving the machine or relayouting might be too expensive. So they decided to just make a kind of a probably a better movement or a better scheduling if we are talking about how we can minimize the max spend and overall the processing time inside the whole process. Then they will just use logical how to say that, you will just kind of like imagine it, and then without changing the layout of the machine, then they will do the production and most of the time probably what they change is the location of this, how the material, the raw material can go in. So for example, if we see here that then to increase the efficiency, obviously part 1 should be go from this and part 2 should be go from here, right? While part 3 and part 4 probably and part 5 maybe should go from the other side. So for example, part 5 should start from here and part 3 should and part 5 should start from here. So regardless which one is again depend on a lot of consideration. It's not gonna be easy. However, if we only consider about the basically material movement, then probably the physical machine layout will be a better option. Now we go to the algorithm to actually produce or make the CMR cell manufacturing. The first one that I want to introduce is the rank order clustering algorithm. Just call it ROC. Basically, this is not Republic of China. This is rank of order clustering. And we will need the machine part indicator metrics that we have before. And then this method will be short the row and column based on these indicator metrics. And if you're interested in this algorithm, you can actually try to Google it, or maybe I think it's in Science Direct. It's King and rank order clustering. It's a paid one, so maybe if you have someone that have access to a lot of journal, then maybe you can go there, or I hope our university have the access. And then this cluster basically will obtain the MC or the machine cell based on the part family, because we are rearranging the indicator matrix. Then we will at the same time we have the part family, we will have also the the machine cell. There are in total gonna be 6 steps to do the ROC. So we will need to remember again our indicator metrics, right? So we will have here I is part, and then we have, where is it? It's gone. We have J, which is the machine. So I is the index for part and J is the index for machine. We will have 1, 2, 3. This is the index, yeah? 1, 2, 3. You mean how we do the clustering? So this is a different type of these data mining clustering. So what Mohsin said about k-means is you try to find the cluster based on the distance, right? When you say the k-means, the means, the average distance from one point to another point, considering a several classification. In this case, we're just gonna use the indicator matrix based on the parts and the data of machine. So why it's mentioned about clustering, because we try to make a cluster, which is actually the cell machine. Okay, so in this case, we will have this indicator metric. So if we review previous slide before, we will have I, which is index for parts that we try to make, and J, which is the index for machine. And then if you remember before, we will have the so-called AIJ, which is a between 1 and 0. So if AIJ equal to 1, it means that there is a part I being processed in machine J. So for example, like this, if this is 1, it means that part 1 here, let's say part A will be, let's say this is Tourette machine, yeah, will be processed in the Tourette machine. So if it's equal to 1. If it's equal to 0, let's say part B is not going to the Tourette machine. So something like that. And what we need to do is first, we calculate the binary weight. BW, BWJ, which is, it means for each column. So for each column, you will need to calculate the binary weight by having this 2 power m. The m means the number of machine. So for example, the m is the number of machine, yeah. For example, in this case, we have in total 3 machines. So m will be equal to 3 minus j. J is the index of the machine. So for example, in this case, for this column, yeah, the binary weight will be 2 power 3 minus the index is 1. So 2 power 2, which is 4. And then we make it all for all columns. So in this case, it's going to be 2, 3 minus 2, which is 2. And then this going to be 2 minus power 3 minus 3 equal to 1. And after having all the binary weight for each column in our indicator matrix, we calculate the D or decimal equivalent by sum all the m for each row, yeah, for each row, for each part, you sum all this value multiply by this, your previous indicator matrix, AIJ, whether there is a process or not in this particular machine. And after that, we rank from largest to smallest. And then after that, once we reorder, if we cannot find the kind of group, then we need to continue to step 4. But once we cannot continue, I will mention how we continue and not continue, then we need to stop. And after doing it for each machine, then we calculate it for each part by calculating the binary weight for each column, same like before. So let's say we have like this 1, 2, 3, and then 1, 2, 3, yeah. Then we calculate the BW for each row. It means here it's also 2. This n is max number of parts, so n equal to 3, right? For this is 3 minus 1, so this is 4. And this is 2 power 3 minus 2, which is 2, and then 2, which is 1. And then we also again calculate the DE for each column J by summarize all the multiplication of the BW with the AIJ. And then we sort from largest to smallest. And once we reorder the columns according to their rank, then if no rearrangement is needed, then we can stop. Otherwise, we return back to the step 1. So here's the example. We start from having this so-called indicator matrix. We have 6 parts with mean n equal to 6, right? And then we have 7 type of machine, which mean m equal to 7. Then we will need to calculate the binary weight for each column J. So this is J, yeah, which is machine, this is I. Okay, so for this one, for example, this is gonna be 2 power 7 minus 1. And there is 2, 7 minus 2, and you calculate it for each of the column. Then once you do that, then you calculate the DE. This is decimal equivalence. So for each row, you will calculate it using this. Right, AIJ. So for each J equal to 1 until M, yeah. So it means like this is 64 multiplied by 1 plus 32 multiplied by 0 plus 16 multiplied by 0 plus 8 multiplied by 1 plus 4 multiplied by 0 plus 2 multiplied by 1 and 1 multiplied by 0. So we got 74. Then you do it for all the row. So 32, so this one is gonna be 32 plus 16 plus 4. And this is gonna be 8 plus 2 and etc. Once you do calculate all the DE or decimal equivalence, you sort it based on the largest value. So once you sort this column needs to be rearranged, the row, yeah, the indicator matrix. As we can see here, some part is being moved according to this DE value. So part 1, previously it's part 1, 2, 3, 4, 5, 6. Now it become part 1, 2, 4, 6, 5, and 3. And as we can see here, there are no cluster yet. You cannot see any cluster or machine cell yet. So we go to step 4 and 5. The step 4 and 5 is the same, but you do it for each row, you calculate the BW binary weight. Okay, like this. So this is 2, 6 minus 1, yeah. Then this is 2, 6 minus 2, and etc. And then again, for each column, you will calculate it based on the DEG, yeah. It's gonna be the sum of the BWI, AIJ for n equal to 1 until n. Sorry, for I, for J, for I, yeah, for I. Okay, so for example, like this, there's only 1. So 1 multiplied by this become 32. And for this one is 16 plus 8 plus 4. And for this one is 16 plus 8 plus 2 and etc. And after that, you got all these binary, not binary, decimal equivalents. And then you sort it based on the largest to the smallest. And it become like this. So for example, M4 and M6 are the largest. So you basically just move it to the left part, yeah? Left is that, yeah, this is left. So we can see here, like this. And then we start to see the shape, yeah. However, we still cannot decide whether it's a cluster or not. So we need to again return to step 1 and 2 to make sure that whether there is can be an improvement or not. So again, we calculate the binary weight, then we calculate the decimal equivalence. And as we can see here, it's not actually short according to the weight yet. So we rearrange it. So according to the previous slide, we can find it like this. As we short it, then we start to see the shape, right? In the step 3. And then we need to make sure that whether there is an improvement or not by again calculating these binary weight for each. This should be I, sorry. So like this, and then you calculate, then you calculate the DE. And turn out after we calculate, we redo the step 4 and 5, we found out that we cannot improve anymore, and so the procedure is being stopped. So as we can see here, it turned out that the part 1 and part 3 are the part family, and then the part 2, 4, 6, and 5 are the part family too. And at the same time, it becomes machine cell 1 and machine cell 2. Okay, so that's the ROC. It's easy, right? Is there any question before we move to another algorithm? It's quite clear.
Yes, it is.
So far, clear, Miss.
Okay.
Yes.
Okay, so aside from the ROC, we have a different algorithm called similarity coefficient. And basically what we do in similarity coefficient is we try to pair a machine or parts and then calculate it using the so-called Jaccard similarity coefficient. In this algorithm, however, the complicated part is if you have lots of, let's say, part and machine that you need to consider. So although the algorithm itself is quite simple, maybe you will need more time compared to the ROC if you have a bigger number of machine and parts. However, it's still being used quite a lot because it's, again, as I mentioned, it's quite simple algorithm. So basically for each pair of machine, they will be, they will try to make a pair and we will calculate the value for each pair to understand whether this pair should be this machine pair should be grouped together or not. And how we do it is using this Jaccard coefficient similarity, where we will have this calculation SSIJ. So the I is a machine I, and J is machine J. Okay, if we have n number of parts that we need to make, we will have this index K. So the part K is the index for part. It's part K, yeah. So the AKI, it's almost the same with AIJ. However, because we have two different machines, then I change it into AKI, will be equal to 1 if part K needs to be processed is in machine I. AKJ will be also equal to 1 and 0 if part K needs to be processed in machine J. Okay. So what we need to do is basically just sum all these AKI and AKJ, which means whether there is a part K going to the process and in each machine or not, and then summarize it and divide it with the sum of this calculation, which is AKI plus AKJ minus this, the multiplication of AKI and AKJ. So to make it better for you to understand, then maybe we can go to the basic algorithm. So basically for this algorithm, you need to make a pair. So let's say you have 4 machines, yeah, machine 1, machine 2, machine 3, and then machine 4. Then you need first you consider every machine as one each own cell, and then you make the machine pair. So for each machine pair, so for example, we will have machine pair 1 and 2, or machine pair 1 and 3, and machine pair 1 and 4, and machine pair 2 and 3, 2 and 4, and then 3 and 4. So we have 4 machines. So it's quite easy, yeah. I mean, like the calculation will be quite easy because you have small number of machines here. So we need to calculate all the similarity coefficient for this pair. That's why I say if you have lots of machines, then maybe it's gonna be a bit complicated if you calculate it manually. And then once we have the SC value for each machine pair, then we will set the threshold, the initial threshold value. And if the SC value is greater than the threshold, then we will make the certain pair as a one cell. So, okay. So the previous relation is being terminated, and then basically we will consider those pair as a one single entity. Okay, and then for each cell generated in step 2 is being treated like a machine, so kind of like a one entity, one machine, and then we need to consider, we need to recalculate the new set of SC value for machine pair, cell pair, and machine cell pair. So if you have the cell pair, so for example, after the first step 2, yeah, step 2, we found out considering the initial threshold, we found out that machine 1 and 2 should be grouped, and machine 3 and 4 should be grouped. Something like this. So we will consider this. First, the cell pair. We need to determine the SG value between each machine in the first cell. So you need to consider the SC between 1 and 2 and SC between 3 and 4, and each machine in the second cell, and use the larger SC value for the SG value of this relation. If you have machine cell relation, it means, for example, 1 and 2 is considered as 1, and then you pair it with number 3. You try to find the combination of this. Then the SG value between each machine in the cell and a single machine. Then we need to use the largest value as the SG value for machine cell pair relation. Okay. So you basically just calculate it as a kind of relation between single to still single machine. And then by using the smallest value, actually we can determine whether 2 machine or cell should be grouped or not. So maybe this is the example. It's gonna be easier when once you see the example. We use the same indicator matrix as before, and then we calculate the SG value using this Jaccard coefficient. But previously, we find the machine pair first. So because we have 7 machine, it means we have how many? 1, 2, 3. Yeah, something like that. And then we will calculate the SC value for each machine pair. And as we can see here, we have, for example, machine 1 and 4 have SC value of half, 1 and 6 half, 2 and 3 half, and then 2 and 5 2 third, and quarters, and another quarter, and then we have several value that is not 0. Then we can make the threshold value. So for example, they decided to have 2/3 as the threshold value. So the machine pair 2 and 5 and 4 and 6 is being grouped as one cell. And this is the calculation, the example calculation for the Jaccard coefficient using this formula, as I mentioned before. So for example, you try to understand the similarity coefficient between machine 1 and 4. So you basically try to calculate it using this. So for example, as we can see here, A11 is here. So 1 multiply by 1, 4, yeah, like this, 1, 4 plus for part 2, 2, 1. So 2, 1 is 0. Sorry, 2, 1 here, 2, 1 is this. Multiply by 2, 4, then 3, 1 by 3, 4, and etc. Okay, and then divided by this. So A11 plus A14 minus multiplication of this. So we got this and we got this. Now it's quite complicated, right? If you miscalculate or something. So that's why some people code it. And then because we already mentioned before that the machine 2 and 5 and machine 4 and 6 gonna be grouped together, we make it as a entity, one particular same entity, same machine. Okay, and then we make a new indicator matrix considering their previous indicator matrix. So in this case, for example, machine 2 and 5, if we see it like this, there are some part that is the same. Like for example, part 2 is being made in machine 2 and 5, and then part 6 is being made in machine 2 and 5. However, only part 4 is being used in machine 2. Regardless whether the part 4 is not being produced in machine 5, they are still, you still put the value 1 here because it's considered as a cell. So you use the one with the highest score. It's the same with the M4 and 6. And then we again calculate the pair. We make the pair and then we calculate the SC value. So the pair is going to be like this. So you pair 1 and 2 and 3, 1, 3, 1, 4 and 6, 7, 4 and 6, 1, 7, and etc. And then according to this, so we need to calculate the SG value based on step 4. So for example, because this is machine and cell, we need to calculate for inside this, plus if we calculate for each, and then turn out it's 0, and then we continue until the end. And for the second threshold, we reduce the threshold to ensure that there will be a new pair in our facility. And so we find out that only 2 additional machine pair is considered here. So for example, in this case, whether it's combined or not, 1 should be combined with machine 4 and 6, while machine 3 should be combined to cell 2 and 5. So then we will have like this, right? The new indicator matrix will be 1, 4, 6, then 2, 3, 5, and then 7 by himself. Okay, and then we again calculate the pair. Let's say you're not satisfied, so you try to calculate the pair like this, and like this, and like this, the possibility. Okay, so you calculate it, and then you find out that machine 2, 3, 5, and 7 is good enough to be combined into one shell. If you consider whether you lower the threshold value or your threshold value is still 0.5, but usually the more iteration you have, you will lower the threshold value. Okay, and then you again ensure that whether you need to stop or not. So you again consider the pair. Basically, how if basically they made into one cell, and turned out they are not supposed to be into one cell, so we stop here. So if we stop here, using we stop here. If we stop here using this threshold value 0.33, then we find out that our result is same with the result when we use the ROC, or the rank order clustering. However, for example, the decision maker feels that the M7 should be put as one particular shell. So rather than become one cell, they are gonna be put outside the cell. So for example, it's gonna be cell 1, machine cell 1 consists of 1, 4, 6. And machine cell 2 consists of machine 2, machine 3, machine 5. Then they will have machine 7 outside the box. Okay, so this dendrograph is just to help to show the possibility of the machine cell considering different type of threshold value. So the question will be, which one is better? Whether you make the machine 7 into the machine 2, 3, 5, or whether you make it like independent entity. And it will be, you can know the result once you actually implement it in the facility. However, obviously, when you make the cell manufacturing system, you try to minimize the movement, and then you try to simplify the process. So if your option is become more complicated compared to the initial one, obviously you shouldn't use that. So I'd say that lots of experience facility designer will know which way to go, because facility layout should be a strategic planning. So even if you move it or you change it, it should be used for quite a long time, maybe 5 years or 10 years period. So the question about which one is better can be answered once you actually implement it in the facility. So this is all for today's class. Is there any question? It's really easy, right? Okay. Okay, I'm not sure whether you heard
Yes.
it or yeah.
This clustering and dendrogram is the same with the determining or different or how?
Oh, sorry, pardon.
We study about this dendrogram, clustering, and this determining techniques, right?
You mean the difference?
Is it same like data mining or other techniques?
Can you type it? It's really unclear in my, how to say that.
Okay.
Sorry. So if I'm not mistaken, I hope I'm not mistaken. So in dendrograph, basically you try to visualize it into a better way, right? And you can only use the dendrograph if, in my opinion, it's gonna be good to use dendrograph if you don't have a big number of data. Well, clustering itself is a methodology to make a cluster, like the Mohsin said. And you also can still visualize that according to the type of software that you use. However, usually the result of the clustering will be a kind of value. In this class, when we do the ROC, we clustering it based on not the kind of value, but rather how to say that. So because what we use is, for example, the ROC, what we use is metric. So we use it in a visualized type of metrics where we actually cluster it based on, I'm not sure how to explain that, based on the possibility of close, rather than the value of closeness. It's more like whether they can be grouped together according to the variable Aij. However, when you talk about, for example, k-means clustering or k-medoid clustering or other type of other clustering, then what you try to calculate is the closeness from several data. So for example, if you try to have a location, for example, and then you have different lots of customer, you can use a certain k-means clustering to actually find out which location is the best to build a facility, for example, like that. Or if you have a different type of classification with different type of data, then you also can use by translating all of this data into and then try to calculate the closeness and which location is actually the best. And for dendrograph itself, in this case, basically you just to visualize what we already have here, where we have several possibility of pairing. And then we can see here that for each pairing, it actually can happen if we have a certain threshold value. So I hope it can answer your question.
Yes, thank you.
So if you learned the data mining technique, obviously there are many types of data mining technique, and even for example, sometimes when I do the facility location problem, I also use the data mining techniques such as k-means or k-medoid because it's easier to do that way. So all these techniques can be applicable to a lot of application. So as long as if you're willing to learn, or if you're kind of curious, then maybe you can read more books, or I don't know, have you got the data mining class?
No, this is no. Yes.
Yeah, so something like that. So I think you will get, there will right, there will be a data mining class, right? I think data mining and what's that? Analisis keputusan apa sih? Yeah.
That's 6.
Yeah. So is there any other question? If not, then I will just read